Have you ever looked at your phone or your computer and just wondered, how? How does this thing work? Well, today we are going on an absolutely wild journey. We're going to follow the story from a grain of sand all the way to the thinking machine that's probably in your hand right now. This is the story of modern electronics. So let's start with a really simple but kind of mind-bending question. How do you teach a rock to think? I mean, it sounds like something out of a fantasy novel, right? But believe it or not, that's the fundamental question we had to solve. And the answer? It starts with silicon, one of the most common things on the planet, the main ingredient in sand and, well, rocks.
All right, to get how any of this is possible, we have to zoom way, way in. I'm talking down to the subatomic level. Because everything, and I mean everything, in electronics starts with the electron. You can think of it as this tiny, super energetic particle that carries information and energy. Its movement, this little dance it does, is the spark for, well, everything we're about to talk about.
Okay, so here's the thing. Not all electrons are the same when it comes to electricity. The ones we really care about are the ones on the very edge of an atom in the outermost shell. They're called valence electrons. And really, their whole job is to decide whether to stick around or to jump over to a neighbor. That one choice, that determines if a material is going to conduct electricity or not. It's that simple.
And that behavior gives us the materials we all kind of know. You've got conductors, like copper wire. For electrons, that's a wide-open 6-lane highway. Go wherever you want. Then you have insulators, like rubber. That's a solid brick wall. Nothing's getting through. But the real magic, the secret sauce for all electronics, is this third thing, semiconductors. They're special because they can be either a highway or a brick wall. And the best part, we can control which one they are. That's the key.
And that brings us right back to our hero, silicon. So why silicon? What makes it so perfect? Well, it's a natural semiconductor, and it has exactly 4 of those valence electrons we talked about. And that number, 4, isn't random. It's the magic number. It lets silicon form this perfect, stable, predictable grid that we can then start messing with on purpose.
So if you just take pure silicon, it's a little boring electrically. Every silicon atom holds hands with its 4 neighbors, sharing its electrons. It forms this perfect, beautiful, stable crystal. It's very peaceful. But for our purposes, it's useless because all the electrons are locked in place. There's no flow.
So we have to get in there and mess it up a little bit. We do this with a process that sounds kind of shady, but it's genius. It's called doping. To make N-type silicon, we add a tiny bit of an element that has 5 valence electrons. Now there's an extra electron that doesn't have a partner, a free agent ready to move. That N stands for negative. Or we can do the opposite and add an impurity with only 3 valence electrons. Now there's a missing electron, a gap. We call that a hole. And since it's the absence of a negative electron, we treat it like a positive charge. That's P.
Now for the big moment. This is where it all comes together. What do you think happens when we take a piece of our N-type silicon with all its extra electrons and stick it right up against a piece of our P-type silicon with all its empty holes? We create something called a p-n junction. And in doing that, we've just built the single most fundamental component in all of electronics. We've made a diode.
So what is a diode? It's basically an electronic one-way street. It's a valve for electricity. Current can flow through it one way, no problem. But if that current tries to turn around and flow backwards, nope, the gate slams shut. This is a massive deal, because for the first time ever, we've made a solid object with no moving parts that can enforce a rule. We have created control.
And we exercise that control with voltage in a process called biasing. If you apply voltage in what's called the forward direction, the barrier between the P and N sides just shrinks away, and poof, the current flows. But if you flip that voltage and apply it in reverse, that barrier gets bigger and stronger and it blocks the current completely. It's our first real on-off switch.
And this little one-way gate has a job that you rely on every single day: rectification. See, the power coming out of your wall socket is AC, or alternating current. It flows back and forth. But your phone, your laptop, they need DC, direct current, a steady, one-way flow. The diode is the first step in that conversion. It basically lets the forward-moving part of the wave through and blocks the backward part. It's the bouncer at the door of every single charger you own.
Okay, so a one-way gate is pretty cool. That's some serious control. But what if we could build a better gate? One that we could open and close with just the tiniest, most delicate touch. Well, that next invention, the transistor, that's what truly unlocked the entire digital world.
The transistor is, and I'm not exaggerating, the most important invention of the 20th century. It is the fundamental building block, and it has two superpowers. First, it can work as an amplifier, take a tiny little whisper of a signal and turn it into a loud shout. And second, maybe even more importantly, it's a perfect electronic switch with zero moving parts.
So how does that amplification thing work? It's all about something called current gain. The best analogy is a giant water valve. Imagine you can control a massive fire hose with a tiny little knob. A tiny, effortless turn of that knob, that's your small base current, unleashes a huge, powerful torrent of water. That's your big collector current. A tiny input gets you a massive output.
And what about that other superpower, the switch? It's just so elegant. If you don't send any of that small current to the base, the transistor is in cutoff. The switch is off. It's an open road. But if you send just enough current to the base, it flips into saturation mode. The switch is on, a closed circuit. And that ability to be either completely on or completely off, well, that's a 1 and a 0. That's the language of computers. So now we've got it. We have our engineered silicon, and we have this tiny, perfect, controllable switch. All the building blocks are on the table. But how do you go from one single switch to the billions, literally billions, you need to make a computer think?
Being able to make one transistor by hand was an incredible achievement, but wiring them together, one by one, you'd need millions. It was physically impossible. The next leap forward couldn't be a small step. It had to be a giant one.
And here it is. This is the solution. I know, it looks kind of crude, right? Just a jumble of wires and blobs of wax on a little chip. But this is the world's first integrated circuit, built by Jack Kilby back in 1958. And the idea was what mattered. It was a revolution. Kilby proved that you could make an entire circuit, the transistors, the resistors, the connections, everything, out of one single solid block of semiconductor.
Kilby's invention didn't just open a door, it blew the wall down. The growth after this was just insane. It was exponential. Just look at this. In the 60s, a chip had maybe 100 components. By the 70s, it was up to 10,000. And today? Today we're putting billions of transistors on a chip the size of your fingernail. That is how we got the power of a room-sized supercomputer from 1970 into the phone in your pocket.
And that's the whole story. That's the stack. It's so logical when you lay it all out. We started with a single particle, the electron. We learned to control it by engineering silicon. We used that to build a one-way gate, the diode. We upgraded that into a controllable switch, the transistor. And finally, the integrated circuit gave us a way to print billions of those switches onto one single piece of sand.
So from a grain of sand to a device that connects all of human knowledge, it is just an incredible testament to what we can build when we understand a few simple fundamental rules of the universe. We literally taught a rock how to think. It just makes you wonder, what are we going to teach it to think of next?